Should be good now. Okay, so we have lambda equals -1 and 1 plus or minus 2i, and that's given. And we want to solve this linear system, okay? System of differential equations. So what we have to do is go through each of our lambdas and try and find the corresponding eigenvectors, right? So let's start with the easy one, which is, well, relatively easy, -1. Okay, has anybody tried that yet? We've got to take the null space of, so what do we do to get this matrix from this matrix? Subtract -1 from the main diagonal, which means add 1, right? We're going to add 1 to the main diagonal, so it's 0, -4, -2, and then -4, -4, -6, and then 4, 8, 8. Does that look right? Okay. So that actually, we're going to have to do a little bit of work on this one to get the eigenvalues and eigenvectors. So I'm going to suggest that we move the bottom row to the top and just divide by 4. I'm just going to do all of that at once. So the bottom row, which was 4, 8, 8, becomes the top row, which I'm going to write as 1, 2, 2. All right. And then in terms of, I'm going to go back to this matrix though. When I add the bottom row to the middle row, so you can play these tricks really quickly, right? You add them together, you get 0, 4, 2, right? Well, that's just a multiple of, actually, another way to think about it is if you just leave the second row, leave the first row, put it in the second row, right? You know that you already have 2 pivots. You have to have a row of zeros on the bottom. Because otherwise, the matrix, remember guys, if you get a matrix that's invertible, then you've made a mistake. So it has to, something like that.
So you have to have the zeros.
You have to have a row of zeros when you row reduce it. That has to happen. Yeah. Okay. So I left the first row as is, but I moved it down. And I took the third row and I put it first. And I know that these 2 rows are Li. So it's not like either of these 2 rows could have been zeroed out, right? The third row, then you can just zero it out automatically. Okay, so now you can start doing your free variables thing. You can let z equal t, and then from the middle line, so let's see, this middle equation is -4y minus 2z equals 0. So if you solve that for y, -1/2 of t, right? Exactly. -1/2 of t. And then to solve for x, let's see, x plus 2y plus 2z is 0. So x is -2 times y, which is t, minus 2 times z. So t minus 2t, that's -t. Okay? And so my first basis vector, I'm going to call this v1. If I bust out the t, I just get -1, -1/2, and 1. Right? Okay. And so my first solution, which I'll call x1, the first of my 3 solutions to the system, is just e to the -t times -1, -1/2, 1. Right? Everybody remember that? The form of the solutions is e to the lambda t times the vector.
Without using the C1?
Not yet, because I'm not ready for the general solution. At the very end, I'll put the constants in front of those terms. Okay. All right. Now, we've got 2 more eigenvalues. The good news about, okay, complex numbers, pain in the butt. However, there is one piece of good news, which is you don't have to do them both. Okay. Let me re-emphasize that. You only have to do one of these 2 lambdas that has come up as a conjugate complex pair. And I'm going to always recommend that you do not deviate, use the positive one. Technically it doesn't matter, you could use either one, but I think for making the process consistent every time, you'll get less confused, you just always use the positive one. Okay, so now the challenge here is coming up with the corresponding eigenvectors. So I have to take the null space of the matrix that I get from subtracting that from the main diagonal of the matrix. So I have -1, and I'm subtracting 1 plus 2i, so that's going to give me -2 minus 2i. And then I still have a -4 and a -2 there. Then I have -4, and then I take -5, and I have to subtract 1 plus 2i, that's -6 minus 2i. And then I have -6. And then on the bottom line, I have a 4, and I have an 8, and I have 7 minus 1 plus 2i, that would be 6 minus 2i. Oh, that is pretty nasty. How did I come up with this problem?
There was one like other something else.
There was one that was this bad?
Yeah.
Okay.
It was a 2x2, but it was pretty bad.
Okay. Well, let's see how this goes.
I'll fuck it.
The one thing, so we have to do some EROs here. The one thing I can do, relatively obvious, is add the second row to the third row, because -4 and 4 will cancel out. Let me just leave the first row the way it is right now. And I also know that at least one row has to cancel out completely, but at this moment I don't know which one. So I'm going to just, I'm going to leave the second row the same. And then I'm going to add the second row to the third row to at least get 1 0 going. When I add this to this, I'm going to get 2 minus 2i. When I add this to this, I'm going to get -2i, right? Something like that. That look good so far? Okay. Goodness.
Does it matter if we like divide everything by 2?
No, we could divide everything through by 2. Yeah, let's just do that. I don't know if it will make a big difference. Actually, let's do this. Let's divide everything by 2, and let's change the signs on the first 2 rows. So I'm going to rewrite the first row 1 plus I, 2, and 1. And then on the bottom row, I'm going to multiply by a negative and also divide through by 2. So I'm going to get 2 and 3 plus I and 3. And then on the bottom line, 0 and I guess I'll leave this one the way it is. 1 minus I and -I. So I'm only going to divide by 2 on the bottom line. Leave everything else the same. If I, okay, I probably won't give you one that's this messy. Okay. This is sort of more than I was expecting. I was just looking at my solutions and I said, it gives rise to the corresponding eigenvectors. Okay. Whatever. What you can do here, if you wanted to, is there is a relationship between 2 and 1 plus I, which is that if you multiply 1 plus I, if you multiply 1 plus I by 1 minus I and FOIL it, you get 1 minus I plus I minus I squared, which is another plus 1. This actually equals 2. So, for example, I could multiply the first row through by 1 minus I. Let's just do that real quick. So, if I multiply the first row through by 1 minus I, then 1 plus I times 1 minus I is 2. And of course I have 2 times 1 minus I would just give me 2 minus 2I. And then 1 minus I right there. And then the second row I'm going to leave it the same. And the third row I'm going to leave it the same. Do what?
Just multiply a row by something?
Yep, you can always multiply a row through by a constant.
Oh,
That's one of our EROs. Yeah. Okay, now I'm going to take, let's see, I guess I'll take the negative of the second row and add it to the first row. Sorry. No, I'll take the negative of the first row and add it to the second row. So I'm going to leave the first row just the way it is, 2 minus 2I and 1 minus I. And then I'm going to take the negative of the first row and add it to the second row, and I'm going to get a 1. Negative of this, add it to that, plus plus 3i, 1 plus 3i exactly. And then the negative of this, and add it to 3, is going to be 2 plus I believe. Okay? And then I have 0, 1 minus I, and minus I. Good grief. I don't see it coming together real nice. I mean, you actually know that a row has to get crossed off, right? And it's not going to be the first row that's going to get crossed off, because I can see that the first row is not a linear combination of the second and third row, because you've got these zeros and zeros and a 2 here. So one of these other 2 rows has to cross off, okay? It's not obvious though, is it, that this row is a multiple of this row? But it has to be. Either has to be or we screwed up, okay? I'm gonna trust that we didn't screw up. Let's cross off the second row. The third row has the nicest possible numbers. Okay. All right, now I'm gonna try to see if I can get my x, y, and z. Now remember, when you have only 2 entries here, do you remember how to do it? This is by the way, this is x is over here. In the bottom row, we only have a y and a z, and we want to get them to cancel out. What you do, you switch them and change the sign of one of them. So I'm going to switch them, and I'm going to put the 1 minus z here, or 1 minus I here, sorry. And then I'm going to put the negative I here, but I'm going to change it to positive I. You guys remember that? So if I have like A and B, and I would like to kill that row with x and y, then what I do is I take x equal to negative b, and I take y equal to a. I just switch the positions of the entries and put a minus in front of one of them. That works for complex numbers as well. And I'm just ignoring the x right now. I'm just ignoring that because I'm only solving the bottom row, which I've just done by this little switch trick. Okay? Don't get it, Bobby? So let me write down the bottom row. The bottom row is 1 minus I times y minus I times z, and we would like to set that equal to 0. That's really the equation we're trying to solve. What I'm saying is that we can solve that by choosing y equal to I and z equal to 1 minus I.
So we can kind of guess.
Yeah, well, it's a guess, but it's an educated guess because you've done it a whole bunch of times where you see that that trick works.
Oh.
That you switch you just swap these coefficients and change the sign of one of them. So I changed the minus I to positive I, and I put the 1 minus I over here. Okay? Now I go back to the first line to try to figure out what x is. Okay, so the first line, I have 2x plus 2 minus 2I times y, which is I, plus 1 minus z times 1 minus I times 1 minus I, and we want that to equal 0. So this is 2x, and let's just multiply this out. This is 2I, and then minus 2I squared, that's like plus 2. And then over here I'm going to FOIL, I get 1 minus 2i's, and then plus I squared, which is minus 1. And nobody can accuse me of only doing the simple problems in the review. It's about as bad as it gets. All right, the 2i and the minus 2i cancel. The minus 1 and the positive 1 cancel. And it looks like x is negative 1. Oh my gosh, that turned out so simple. After all that work. And that is what I got on my solutions, so I'm excited. Okay, everybody with me so far? Go ahead.
Why did you cross out that middle row?
Well, I knew that I have to be able to cross off at least one row. Whenever you do these eigenvector computations, you know that your matrix right here, if I ask you what's the determinant of this matrix, you should tell me it's 0 right off the bat. Because I plugged in a lambda that was given to me, so I know that this has to be a determinant 0 matrix. That means that when I do EROs, some row has to get zeroed out.
Doesn't matter which one.
And it doesn't matter which one, but my point was that it's not the first one. That's the point I made earlier, because the first row actually is the only row that has has any information about x in it. So there's a 2x here. This row is clearly not a multiple of these two rows. So the first row is Li. When you are zeroing out a row, you are saying that row is LD. It's already captured by the other rows, right? I know that the first row is not captured by the other rows, so I'm not going to cross that one off. It has to be one of these two rows that are just LD somehow. And the point is we don't know which one, so we can cross off either one, because one of them has to be crossed off.
You get the same answer.
Yep, you get the same answer. It doesn't matter which of those other two you cross off. Normally it's not this difficult. This turned out this is a fairly messy example, but what can I say?
And we don't have to do it with the idea of having like pivots and free variables, because like right here they didn't use any free variables.
Right. We're just starting to go a little quicker with it. We're not necessarily writing out all of our ERO steps and what all of our pivots are and so on. Okay, so what we get this time is we get a vector, well, I'm going to just go straight to x2. x2 of t is e to the 1 plus 2I times t times the corresponding vector, and the corresponding vector is over there, and it's negative 1 I and 1 minus I. Okay? Now, that may look, at the moment, that may look like only one solution. But it actually is going to produce two solutions, and we need two more solutions. Remember, we've already found one solution right here. We need two more solutions, and I claim that I can get two solutions from that. And this is what you guys did in the homework that you turned in yesterday and what we practiced on Wednesday briefly. But let's practice it again. What you need to do, let me just write it down one more time so I have plenty of room here. You have e to the 1 plus 2I times t times the vector negative 1, I, and 1 minus I. Just recopying it one time real quick. What you need to do is you need to sort of expand this thing in terms of sines and cosines. Now, in this case, notice that if you look at this exponent, remember guys, there's properties of exponents that I expect everybody to know. When you have e to the a plus b, that's just e to the a times e to the b. So when I look at this thing right here, this is really e to the t times e to the 2it, right? And then the other thing I want to do, so I'm kind of trying to split that up. At the same time, I want to split up this vector as well. Maybe I'll do that in the next step, actually. So let me just leave it the way it is for one more moment. So I split up my exponential function, and I recopied the same vector down again. Now, on the next step, e to the t, we're going to be carrying that through all the way. But the e to the 2it, that's where we use the Euler formula. So everybody needs to know the Euler formula. E to the I theta is equal to cosine of theta plus I times sine of theta. Everybody remember that? That's a big one that we've been using. Cosine of theta plus I times sine of theta. Okay? So if I use that right here, what is my theta that I'm going to be thinking about?
2IT.
I still haven't heard the right answer.
2T.
2t, right? The I is not the part of the theta, right? Okay, so it's 2t. So we're going to get cosine of 2t plus I times sine of 2t. All right? And then the vector also breaks apart. Guys, when you're breaking the vector apart, you also want to think of it almost like you're busting out the variables again, except there's no variable. There's just an I. So you're going to have two parts to this thing. One part is going to have the real components of each slot, and the other part is going to have the imaginary components of each slot. So in the first entry, I have negative 1, and that's certainly real, and I don't have any imaginary number in the first position. So in other words, -1 just goes here, there's no I in front of that, okay? And then on the second row, I have something that's purely imaginary. There's no real piece, and there's one factor of I. Agreed? Then in the third row, I have 1 for my real part, and -1 times I. Does that look okay? Everybody with me? Now what you have to do is, first of all, I like to factor out the e to the t. Give yourself a lot of room. You have to do this magnificent FOIL, right, that we were talking about on Wednesday. So the first term times the first term. So it'll be cosine of t times the vector -1, 0, 1. Okay, so the first times the first. Oh, cosine of 2t. Yeah, thanks, sorry. Cosine of 2t. Good. Okay, and then I'm going to do the last times the last next. And the reason I'm doing that is because I have an I times an I, which becomes -1. Very good. So it actually changes to a minus then. I've got -1 times sine of 2t times the vector 0, 1, -1. So I have all of that. Make sense? And then plus my other two terms of my FOIL both have an I in them. So I want to put that down first. So if I do the first times the last, right, that's the outer section. Hey, you made it. How you doing, Greg?
Yeah.
Relatively good?
Yeah.
Should get some bonus points for coming to a review session after being stuck in an elevator. Oh, man. So did they say anything about, like, are they fixing it, or?
Yeah, he was there. I didn't quite make it all the way to the 5th floor.
Okay.
They had to open it and then had to like take a big step.
Oh, golly. Well, good for you. We're glad you're here. Okay, so now I'm doing the outer term. So that's going to be cosine of 2t times the last piece, which is 0, 1, -1. And then plus the inner term, which is going to be sine of 2t times the vector -1, 0, 1. Kind of running out of room there. Does that make sense? Okay, let me write down then. So we got x1 right here. We actually have two solutions here. Do you guys remember on Wednesday I explained that? You have the part without the I in it. That's one of our solutions. And then you have the part that does have the I in it as another solution, but you're going to extract the I. You're not going to write down I. Your final answer, guys, cannot have I in it. So let me just actually write down what those two solutions are. We have, basically, I'm going to call it x sub 2, well, I'm just going to call it x2 of t. x2 of t from right here. E to the t times cosine of 2t times -1, 0, 1 minus sine of 2t times the vector 0, 1, -1. Period. Right? Stop right there. And then my next solution, which is x3, don't forget the e to the t. That's coming with you everywhere, right? E to the t, and then we have, I'm going to go over to the second part, and I'm going to write everything down except the I. I dropped the I part, so I'm going to get cosine of 2t times 0, 1, -1, and then plus the sine of 2t times the vector -1, 0, 1. Okay? We have x1, x2, and x3. Notice there's no imaginary I anywhere in any of these expressions now. Make sense? So what do we have to do next? Put it all together. That's all we got left to do. Putting it all together. So the general solution now, this is the last part, is just where you write down x of t as a linear combination of the solutions you have. So c1 x1 plus c2 x2 plus c3 x3. You're welcome to do that as long as you're not being sloppy and I can figure out where your x1, x2, and x3 are. If you don't want to recopy them, that's fine, although there's not going to be any rush. So if you want to take your time and write it out again, you can. Does that make some sense? Everybody good with that? Okay. Awesome.
And you don't want to be
Yeah, you can combine these expressions like the. Remember, you're really reading 3 lines here, right? You're reading the top line, the middle line, and the bottom line. And each of them can be simplified into a single expression. But you don't have to. I, in fact, almost prefer it kind of split apart because I can still see my, pieces of my eigenvectors and my eigenvalues and so on. So, but it's totally optional. I did, that was only in a 2x2 case. I might ask you to do that. I wouldn't ask you to do it for this, because this would require 3 dimensions. Yeah. Oh, let me go over that. Could I, let me just see here. Could I go over that on a slightly different, no, that's not actually a good example. Yeah, I can go over that. Let me go over that. Okay. It's not in the review packet though. The question is, what about sketching the graphs when you have sines and cosines? It's a good point. Let me see if I can dream up something here. Actually, what I might do, I don't really want to just do that problem. I want to give you something new. Let me give you, let's work on a different problem first, and then I'm going to come back to that, so we don't waste too much time.
Do you have to graph stuff on the test?
Yeah, I might ask you to graph something. Let me give you an example. Let me go to number 5 on the review sheet.
There's one on the sample.
And there's one on the sample. Yeah, there's some good examples. So here's an example. Draw a phase portrait. That's what it's called. Remember that big giant picture I drew on the board the other day? For the system x prime equals ax, where capital A is the matrix -6, 1, and 6 and -5. So let's start with this one, and then I'll give you another one that I'll try and find one that has a nice imaginary set of solutions to it. Okay? So if I want to draw the phase portrait, what would be the first thing that I would have to do? Right. I have to find my eigenvalues and eigenvectors, right? Okay, I think I found one I can use. Okay, so I have to find the eigenvalues and eigenvectors. This is just a 2x2, so that part's usually pretty easy, right? We just take the determinant of -6 minus lambda, 1, 6, and -5 minus lambda. Okay, and this is going to be -6 minus lambda, -5 minus lambda, and then -6. And if I multiply that out, I'm going to get lambda squared plus 6 lambda and plus 5 lambda. That's plus 11 lambda. And then plus 30 and minus 6 would be plus 24. Okay? Anybody know how to factor that? Lambda squared plus 11 lambda plus 24.
Plus 3 plus 8.
3 and 8, right? That's exactly right. Lambda plus 3, lambda plus 8. So this